Thanks, John. Welcome, everyone. As John said, this webinar is on the impact of uncertainty on industrial flow measurement. It will cover essentially some basics in uncertainty and look at how that impacts flow measurement, and it will also have a few examples. So it's mainly aimed at people perhaps with some understanding of uncertainty, but would like to know more on how you would apply various theories and take that through towards calculations and also developing your own budget. So if you take a look at the first slide, we will go through basic uncertainty theory initially. So this will look at various terms that are used on uncertainty theory. We'll then go on to look at the cost of errors. So this is just a few examples explaining why uncertainty in a sense is important. After that, in the third section, we'll look at types of uncertainty, how you derive uncertainty values based on the information you have available. And then we'll go on to look at various calculation stages for if we're doing an uncertainty calculation for a given parameter. And then section 5 will round everything off with a few practical examples, and that will hopefully reaffirm what we went through in the first 4 sections. So the reason essentially why uncertainty is important is that making measurements, it's only an estimate of the true value, and it does not give the true value itself. And as it says here, the true value is unknown. So if you think of using weigh scales or a stopwatch or looking at your car speedometer, all these are doing essentially is estimating what the true value is. And as it says here, it does not give the true value itself. So then we go on to what is uncertainty. So this is an interval either side of the measurement result where you would expect the true value to lie. And if you look at the indicated value in the graph here as an example, this will be your indicated value from whatever device you're using to measure something. As it says, it can be scales, a flow meter, your car speedometer. That value will have an associated uncertainty to it. And you would expect the true value to lie somewhere either side of the indicated value in the stated uncertainty bands that you're given with a given confidence. So the confidence level, this is important. This is the likelihood that a real value of a measurement will lie within a specified interval. So the larger the interval, the higher the confidence that the true value will lie within it. And this makes sense. If you expand either side of the indicated value, you're increasing the chances that the true value will lie within there. So when you have a measurement result, there's 3 things you need to state. You need to state the actual value from the measurement, whether it be a flow meter, a thermometer, pressure gauge. You need to state the uncertainty in that value, and then finally the confidence level associated with that uncertainty. And as it says here, an example is this is a flow meter in this case. So the result of a flow measurement may be stated as 3.5 plus or minus 0.2 litres per second with a 95% confidence. So what does that mean in reality? It means that we have taken a result from a flow meter or some other flow measurement device. The value indicated by it is 3.5, but based on our uncertainty analysis, there is a 95% chance that the true value will lie somewhere between 3.3 and 3.7. It also means that there's a 5% chance that the true value will actually lie out with these limits of 3.3 and 3.7. Error is another term that's commonly used. Definition of an error is the difference between the true value and the measured result. The true value, as I described in slides before, is unknown, but you do see error used at times. And when you do see error used or error value stated, it's sometimes in reference to a low uncertainty standard. So you may have a high accuracy PRT or flow meter, and you will be testing another flow meter against it, and then you will quote the value against the meter or device with a low accuracy or a low uncertainty. So accuracy, this is how close there is an agreement between the result and the true value. You can have an accurate measurement with a larger uncertainty. So in a sense, you may be lucky and be close essentially to the true value with a measurement that has a larger uncertainty. An important point is you can't attach a value to accuracy. It's a qualitative term. So you can say, for example, this device is more accurate than that device. But when you attach a value to accuracy, you're actually speaking about uncertainty, and you subsequently will need to state a confidence level with that stated uncertainty. There's many examples when you look through brochures of products and devices. They will state an accuracy of 0.2% or another value, and they'll have no confidence level given or nothing else. So what you should state is an uncertainty with a value and also with a confidence level to that uncertainty. Repeatability is another term commonly used. So this is the closeness of agreement between successive measurements under the same conditions at the same time. So as it shows here in the little figure on the left, this is a repeatable device as it repeatedly gives very similar results, one after the other. So on the top left, you can see a device. It has good accuracy. If something has good accuracy, it consistently needs to be close to the true value, and then hence that must mean good repeatability. If you have poor repeatability for a device, you will have poor accuracy. You may strike lucky with one or two measurements, but if it's not repeatable, it will be close to the true value for some, perhaps, and not close for others. Finally, good repeatability doesn't necessarily mean good accuracy. You can have results that are very repeatable, but not close to the true value. And that leads on nicely to bias. And this is when essentially all the results are affected in the same way. So an example is you could have a very repeatable device with a bias either way. You can correct for bias, but you need to consider the uncertainty in that correction. So we'll next go into a few examples looking at why uncertainty is important and how essentially things can cost if you don't have a good uncertainty calculations or drive down uncertainty low enough. But I think the main takeaway from section 1 is that when you're stating an uncertainty, you need to state an associated confidence level with it. So in 2022, there were approximately 81 million barrels of oil produced per day, and that would be a total cost of $7.27 billion, assuming that price on the bottom of $89.79. If the uncertainty in the amount of oil produced was 0.25% at a 95% confidence level, this would lead to a financial exposure of £18.2 million per day. So what does this mean? It essentially means that there is 95% confidence that the exposure financially would not be more or less than £18.2 million per day, based on a 0.25% uncertainty and amount produced at a 95% confidence level. There is a chance, a 5% chance based on the uncertainty analysis, that the exposure can be more than £18.2 million per day. So this is why, in a sense, it's important to drive down uncertainty as much as possible, because that's not an insignificant sum of money. Perhaps an example that's more relatable to everyone is the cost of uncertainty in refueling a car. So if a fuel tank has a capacity of 50 litres, the uncertainty in filling the car, was 2%, the uncertainty in litres would be 1 litre. So the uncertainty in filling the tank would be plus or minus 1 litre at a 95% confidence level. If you assume £1.45 per litre, that would mean the cost of filling a 50 litre tank would be £72.50, plus or minus £1.45 at a 95% confidence level. If you assume you fill your car once per week, that would be 52 times £1.45. So as it says here, an exposure of up to £75.40 per year at a 95% confidence. So again, what this means is that you or the petrol station should not be exposed to more than £75.40 a year. So you shouldn't gain or lose more than £75.40 per year. And there is 95% confidence that will happen. There is 5% chance, again, that you could gain or lose more than this. So the next section will go over the different types of uncertainty. We've spoken about uncertainty and the cost of errors, but this will hopefully give an idea of where uncertainty values come from and how we derive them. So there's two real types of uncertainty in an uncertainty analysis. There's type A and type B. Type A is using real data when we have data available to us, and type B is more along when we have, and in the absence of real data, we need to use other means to estimate uncertainties. So, as I said, type A, we can look at that first of all. This section, and actually most of the webinar, in fact, will use material from the GUM. So this is a guide to expression and uncertainty in measurements, and it's essentially recognised as providing standard methods. This is free to access and free to download, and essentially it really just touches on the concepts detailed in this guide. And it's in the section on type A uncertainty is taken from the GUM essentially, and the theory behind it. So type A analysis is essentially a form of analysis of repeat measurements. If you repeat a measurement, you reduce the chance of error, but repeats never tend to agree. How do you decide which value to use, and what does that variation in the value actually tell us? So the best estimate of a true value is the average of the points. So if you've 10 points here, and you take your average, and that's denoted by the red line shown. If you want to characterise or determine how spread out the values are, you could use a range, as it says here. You could take the highest and the lowest value and subtract one from the other. However, this is insensitive to what's going on in the middle and only characterises 2 data points. Essentially, the standard deviation is a measure of how spread out the numbers are, and that characterises the deviation of a set of values. And as it says here, you can illustrate this with an example. If we have a flow meter, we take 10 readings of a flow of oil, and we get these results in the table below. So values ranging from 73.1 to 73.9. So the equation on the left-hand side is how you calculate the standard deviation. The first step is calculating the average of all the points, and that is our X bar in the box in red. And we then subsequently take the difference of each point from the average. So the average is 73.52, and we have our various flows indicated by the device from 73.1 up to 73.9. We subsequently subtract the average from each of those values to get the difference in the green row at the bottom. The next stage in the calculation, shown in the red box again, is to square these values. We essentially square the values in the green row. From there, we sum each of the values in the squared row. Essentially sum these together. So the sum of the squared values is 0.576. The next stage is dividing by n minus 1. So the reason in this case we are dividing by n minus 1 is what we are trying to do is characterise the standard deviation of a population of flow rates. We only have 10 flow rates available to us. If we were only trying to characterise the standard deviation of those particular 10 results, we would simply divide by n. What n minus 1 is it's known as dividing by n minus 1 as opposed to n is known as Bezel's correction. And what this does is it takes into account the fact we don't have all the data available to us. We only have 10 values in what would be a whole population of values. So the fact that we don't have all the information available to us, it divides by n minus 1 and reduces the value in the denominator. And this actually increases the standard deviation to account for the fact that we don't have all the information available to us. This is simply a correction factor. So as we divide by n minus 1, we've got 0.064. And then the final stage is to take the square root of that value, which is 0.253. And that is the standard deviation of those values for the whole population. So what does this value actually tell us? We've got our 10 results here. What you find is that data tends, if you gathered more flow rates, you would progressively see it cluster in a distinct pattern. And if you keep going, as it says here, note the pattern emerging. What you would see if you continually collected readings, that you would see a high number of readings around the average, and as you go either side of the average, the frequency of the readings would tail off at extremes. And this is a pattern that's seen throughout nature. For example, people's weight, people's height, and things like that as well, where you get this distribution where most is around the average, most of the frequencies are around the average, and as it tails off to the upper and lower distributions. So when we get one of these normal distributions, the standard uncertainty, as it says here, is the uncertainty at the lowest confidence, and the likelihood of finding the true value in this interval is 68%. Most important point probably is on the right hand side. It says standard uncertainty is equivalent to one standard deviation. So our standard deviation of 0.253, I think it was. So we have taking that back to an example, we have our average flow rate of, I think it was 72.53. What this standard deviation we've calculated tells us is the average value of 73.52, I think, plus one standard deviation, and the average value again minus one standard deviation. If we had a full population of data available to us, we would expect 68% of the values to fall within the average value plus one standard deviation and the average value minus one standard deviation. So that's what the standard deviation calculation is essentially doing. It's characterising the spread, or essentially the width, of the normal distribution curve. So expanded uncertainty, different to standard uncertainty. This is an uncertainty at a higher confidence level. It says here that the uncertainty of finding this interval, true value in this interval, is typically 95%, but essentially you can multiply it by any factor you want to get a expanded uncertainty. So if your standard uncertainty is at 68% roughly, you multiply it by 1.96 to get to a 95% confidence. This makes sense. You want to have more confidence that the value would lie within these two bounds, so you would need to multiply your standard deviation. You can use any number in between, but 95 is typically used. If you want to go down to 90, that will decrease the value further. Yeah, and as it says here, when it's plus and minus one standard deviation, there's a 68% confidence that a value would lie within there. And here are a few other selected confidence levels and subsequent coverage factors you would need to use to multiply by to get to that given confidence level. So now we spoke about type A analysis, which is essentially using data you have available to characterise the spread of data, and then subsequently using that spread of data to determine uncertainty values in the data or for a given parameter. Sometimes you might not have that information available to you. You don't have a raft of data available to determine uncertainty. So this is where type B comes in. As it says here, not all uncertainty comes from type A analysis. You often need to assess uncertainty from other sources. So this could be using your own judgment, using a data sheet from a manufacturer. You may buy something from a manufacturer that defines the uncertainty and gives the confidence level, or some form of calibration certificate. So if you're using a PRT or a pressure transmitter, and you've had it calibrated, you should have the uncertainty and the confidence level stated on the calibration certificate for that. Typically, it's the uncertainty stated at a 95% confidence level, but it should always be stated for avoidance of doubt. In this case, to get back to your standard uncertainty, you determine your coverage factor as a divisor and then divide by the uncertainty to get back to a standard uncertainty. Yeah, and this just illustrates it here. You have your expanded uncertainties on the top, and you divide by k, the appropriate k value to get back down to your standard. Yeah, this is again just for a normal distribution. It's going back to what we showed previously. For values that you know are repeat measurements, you may not have the data available to you, and it might be a type B analysis. But if you know it's a repeat measurement, you should use a normal distribution and divide by the appropriate coverage factor, as I said previously. And here are a few, again, coverage factors and confidence levels. It may be that k is stated, the value of k is stated as the confidence level, and that's fine. You can just divide by k, or a confidence level is stated. If a confidence level is stated, you need to subsequently get k from a table, essentially. Not all distributions are necessarily normal distributions in uncertainty analysis. It may be that you know the value lies between two limits with equal probability. So a great example of this is instrument resolution. It's a pretty obvious one, okay to wrap your head around, that if an instrument is poor resolution, it may be being above or below that, but it's going to round up to that value. And it's the probability of it being closer to the value than it is either side of the limit isn't greater. So you would assume a rectangular distribution in this case. And also acceptance criteria and tolerances when, for example, things or piping has been manufactured to a given tolerance, so that essentially it's accepted if it's manufactured within two limits. There's no greater probability that it's around the middle of the limit, but it could be equally either side of the limit based on the manufacturing tolerances. And as I says here, this is a good example, resolution uncertainty. So if you had a flow meter and its measurement was 35 of whatever units it's reading out in, essentially the meter will read 35 if it's anywhere between 34.5 and 35.5. And there's no greater probability that it's nearer 35 than it is to the extremes of 34.5 and 35.5. And because of this is why a rectangular distribution should be used. And from the equation in the previous slide, we can calculate a standard uncertainty. So it would be the difference in the limits, so 35.5 minus 34.5 times a half and divided by root 3, and that would give a standard uncertainty of 0.29. If you would like to reduce that uncertainty, you could increase the resolution of the flow meter. And now it would only read 35.0 if it was between 34.95 or 35.05. Again, you would go through the same calculation stages, and that would give you a standard uncertainty of 0.029. And you can see in this case why increasing the resolution uncertainty or reducing the resolution uncertainty can be done by essentially increasing the number of decimal places given in the output. So section 4, this will look at, it's just a few slides on section 4, but it just looks at what the uncertainty calculation stages are. At the National Engineering Laboratory, we do a lot of calculations like this to characterise our facilities and also test meters that pass through our facilities. We develop a template for calculations, and we go through various stages to determine the overall uncertainty and the parameter we're trying to calculate. So hopefully this, and then leading into the practical examples, will give you a flavour of how you would go about building an uncertainty budget. So the first step is to identify all of the uncertainty sources. You may be using a calculation to calculate a given parameter. So in this case, you would have to look at all of the sources, all of the parameters in the equation, and then consider the uncertainty of each of these parameters. And it may be that you have more than one source of uncertainty, and it's likely that you'll have more than one source of uncertainty per parameter. After identifying all these sources, you estimate the magnitude of the uncertainty. So this takes us back to section 3. You may have data available to you, actual numerical data, that you can calculate standard deviations, etc., do some form of type A analysis. Otherwise, you may have calibration certificates, manufacturing specification sheets, where it's more of a type B analysis, and in some cases you may need to use your judgment as to what you think the uncertainty in that value is. Stage 3, you subsequently convert the uncertainty back to standard values. So this will depend on the coverage factor or the confidence level, and also the distribution itself, whether it's going to be a normal distribution or a rectangular. That's what we always deal with, is mostly rectangular and normal distributions, predominantly normal. The next stage is calculating the sensitivities. So if we have an output that we are trying to calculate from a given equation, we need to calculate how sensitive the parameter is in the equation to the output parameter in the equation. And we'll touch on this in the practical example, and it will make a little bit more sense. Converting to output values, this is essentially multiplying the value of the standard uncertainty in stage 3 by the sensitivity coefficient in stage 4. Stage 6 is estimate the degree of correlation. Again, I'll touch on this in later slides, but only briefly. Correlation is quite a complex subject, but I'll give a few pointers as how to deal with it initially. You don't need to necessarily always take it to a high degree of complexity with correlation. But more information correlation is given in the GUM, which I mentioned earlier. You then combine using the appropriate method, so this refers as to whether it's correlated or uncorrelated. We use a root mean squared method for uncorrelated measurements, and for fully correlated measurements, you add the uncertainties for the parameters together, typically. And then finally, after you've combined it, you express the standard uncertainty for your output parameter at whatever confidence level you want to express that at. So now we can take a look at a few examples, and hopefully this reaffirms what's been said in the first 4 sections. And hopefully, if you have any problems or questions regarding uncertainty, it may help you with any of your challenges you have in terms of developing a budget. But we can dive in. So the first example is looking at an orifice plate. So I presume most of you will know what an orifice plate is, but for those who don't, it's essentially a differential pressure flow device, and you can determine the mass flow rate through the orifice plate with the equation at the bottom there. It's essentially a hole machined in a plate. You get your pressure drop across the plate, and you can, as I said, determine mass flow rate. I wouldn't concern yourself with the derivation in the equation in the bottom, but what our problem is here is we are trying to evaluate the uncertainty in Q, but there are uncertainties in all of the parameters in the equation in the right-hand side of the equation. So what parameters do we have? We've got beta, which is the ratio of the orifice diameter D2 to the pipe diameter. We have the discharge coefficient. So this looks at the ratio of actual mass flow rate to ideal flow rate through the orifice and accounts for frictional effects. We have epsilon, which is the expansibility. Pi is just a constant. D2 is our orifice diameter. Delta P is the differential pressure measured via the U-tube manometer, shown in the diagram on the left-hand side, and rho 1 is our upstream density of the fluid, and this will be dependent on pressure and temperature. So our challenge here is to determine what the uncertainty is in the mass flow rate Q. So the first stage is to identify all the parameters that are feeding into the calculation of the mass flow rate. So we have our discharge coefficient of 0.6, our expansibility factor epsilon of 0.997, pipe diameter of 0.5 meters, our orifice diameter of 0.3 meters, a pressure drop of 50,000 pascals, and a density of the fluid, upstream density of the fluid, of 48.7 kilograms per metre cubed. And that rather nicely gives us a calculated flow rate of 100 kilograms per second. So what we want to know is, what is the uncertainty in that value? Stage 2, we then have to identify all of the uncertainties, associated uncertainties with each of the parameters in the equation. So the first two highlighted in green, these are stated as relative uncertainties. So the uncertainty in discharge coefficient stated here is 0.5%. So this could be through calibration or through the various standards based on the manufacturing tolerances of the orifice plate. Expansibility factor, so this will be a fluid property, will be based on pressure and temperature, and there's also will be an equation fit of data. So this is the uncertainty stated in the expansibility factor is 0.027%. You can convert to an absolute uncertainty U, so back to for discharge coefficient 0.003 by multiplying the 0.5% by 0.6. So 0.5 divided by 100 multiplied by 0.6, we'll get 0.003. If you take a look further down, the pipe diameter and orifice diameter, the absolute uncertainty, and those are 1 times 10 to the minus 4 and 1 times 10 to the minus 5 respectively. You can get those values in relative terms or in percentages by simply dividing this uncertainty, the absolute uncertainty, by the value. So dividing 0.001 by 0.5 and then multiplying by 100. The final two are the pressure drop and density. So the pressure drop is stated as a absolute uncertainty. It's highlighted in red because this will be a derived uncertainty essentially. As I said in the slide before, it's calculated via YouTube manometer, so the pressure drop will be rho GH depending on the height differences in the fluid, the density of the fluid, and also the force due to gravity as well. So the main uncertainty sources here will be the height difference in the fluid and also the density of the fluid at the given temperature and pressure. So these will have associated uncertainty values, and a separate calculation will essentially feed in to this to calculate the uncertainty and pressure drop. And it's similar for density as well. Upstream pressure and temperature will be measured, and an appropriate equation fit will be used to estimate the uncertainty and density. And so both the temperature and pressure measurement as well as the equation fit will have an uncertainty. So there will be a separate uncertainty calculation feeding into to determine the uncertainty of 0.3% for density. So stage 3 is convert back to standard uncertainties. For most of them, we are dividing by 2 here. It's a coverage factor of 2. So discharge coefficient, expansibility factor, pressure drop and density, we are assuming it's some form of normal distribution. We are only dividing by 1.73 for the pipe diameter and orifice diameter. So the uncertainties are 1 times 10 to the minus 4 and 1 times 10 to the minus 5. They may be, for example, manufacturing tolerances. So we are, in this case, are assuming a rectangular distribution. So we're dividing by root 3, so 1.73. The result of this is that the standard uncertainty calculated is a bit higher as opposed to dividing by 2. But that makes sense because we are essentially less certain where the true value would lie. If the results were more, the frequency of readings was more around the middle, around the average of the points, we'd have greater certainty. So that's why we divide by 2 for the normal distribution as opposed to 1.73 for the rectangular which gives a higher value, because there's a greater chance that you may be at the extremes of these limits. The next stage is calculating the sensitivity coefficient, and as I said, this is how sensitive Q, the flow rate, is to, for example, a change in the discharge coefficient. So one option would be to partially differentiate the equation. So you could partially differentiate dq by dc, and then you would subsequently enter all of the other values into the equation, and that would give you your sensitivity coefficient. In some occasions, it's more difficult to differentiate the equation. For example, beta to the power 4, the square root of it, 1 minus it. So the way you would do this was you would keep all, for example, for calculating the sensitivity coefficient of any of the parameters, instead of differentiating it, what you can do is, let's take discharge coefficient again. You would take the value of 0.6, you would add one standard uncertainty, and you would keep all of the values, all of the other values in the equation constant, and calculate the flow rate. You would then take the value of the discharge coefficient again, 0.6, and subtract the standard uncertainty of 0.015 and calculate the mass flow rate again. And essentially what you're doing there, you would then look at the difference in calculated mass flow rates divided by the difference in used discharge coefficient. So you're essentially getting delta Q divided by delta C, and that would give you around 167. And that's just looking at essentially how dependent the output flow rate is on each parameter. So we've did that in column 4 for all of the parameters, and then in column 5 we essentially multiply U, or column 3, by column 4 to get it in the output units, so to speak. In this case, we're assuming nothing is correlated. So what we do here is square each UC term together. So we get the column on the far right, and then we subsequently sum them together, and that gives us 0.0711. From there, you take the square root. If you work back from right to left, that gives you 0.267. It's already in the correct units because we've used the sensitivity coefficients, etc., to get it in the correct output units. So the C is 1, so our standard uncertainty is 0.267. And then when you use a coverage factor of 2, you can use anything you want, but if you want to use a coverage factor of 2, so that's just more than 95%, that would give you an expanded uncertainty of 0.533. So essentially what this means is, based on the uncertainty analysis and the calculated flow rate, the flow value is 100 kilograms per second, and the uncertainty is plus or minus 0.533 kilograms per second at a coverage factor of 2, which is just above 95% confidence in that. So another example here is looking at the volume of a cylindrical storage tank. So the volume is essentially just the volume of a cylinder, so pi d squared h divided by 4. What we want to do is standardise the volume of the tank. We may measure the height and diameter at different temperatures. It may be cold one day or warm the next. So we use an adjustment. So V measured on the right hand side, on the numerator of the right hand side, is what we have measured using our height and diameter measurements. We would subsequently divide this by 1 plus the cubical expansion coefficient multiplied by your measured temperature at which the height and diameter is measured, minus 15. So in this case, we've put a budget together again. We don't need to go through the steps this time, but it's the same. It's identifying the sources, selecting the appropriate coverage factors, getting your standard uncertainty, then getting your sensitivity coefficient, etc. What I would note here is that in the last example, we didn't have more than one source per parameter, but now you can see for the diameter, the determination of the diameter, there's a few sources of uncertainty. So there's a drift with time, there's a determination of the diameter, and there's also a calibration uncertainty. And similarly, there's multiple uncertainties for the measured height of the tank. And the uncertainty value is 3.188 in whatever units are used. The reason we've looked at this example is that suppose the value, your uncertainty value of 3.188 is too high for whatever reason. The easiest way to do this is essentially look at your values down your UC squared column and look at what is the largest value. And if you can reduce the largest value here, it will have the greatest impact in reducing your overall uncertainty. It may be that you can't reduce your largest value, but as you go down the values in the UC squared term, reducing them will have a progressively less and less of an impact. But suppose we can reduce the uncertainty and the calibration of the diameter. So if we halved it from the expanded uncertainty from 0.048 to 0.024, we could, as you can see, we could bring that uncertainty down to 2.720. If you want to bring it down further, you would again, after you do that stage, is identify the next largest source, or the new largest source. So that would be the calibration uncertainty and height. So if you halve that again from 0.1 down to 0.05, you can reduce the uncertainty further. And again, if you want to reduce further, look at the next highest source, that's in the determination of the diameter. And you can progressively reduce the value by looking at that. So that's a reasonable example as to after you do your uncertainty analysis, if your value is too high, it gets you to prioritise the sources that will have the biggest impact on the budget itself. So I've got a few slides in correlation. As I said, I don't go into it in too much detail because it's quite a complex topic. But essentially, when something's uncorrelated, like we've assumed in our examples, in the last two previous examples, the root mean squared method of combining uncertainties like we did, so that's taking the UC squared terms together, summing them, and then taking the square root. It takes into account the fact that the measurements were independent of one another. They may be at different parts of the uncertainty range. One uncertainty may be, so for example here we can look at the two flow meters. One flow meter is overreading and one flow meter is underreading. So if we simply sum the uncertainties together, you would end up with an unrealistic or overestimation in the total uncertainty. So the root mean squared method of squaring the values and then taking the square root, summing them and then taking the square root of each values, takes credit for the fact that for a number of parameters, independent variables, that they may be at different parts of the measurement range, and it's likely that some will have an effect of increasing the output parameter and some will have an effect of decreasing the output parameter. And this is how we can take credit for that by doing the root sum squared method. The value calculated via this method will be less than what would be if you simply summed the uncertainties together. But if we consider correlation, if the measurements were made by the same meter will be out the same either way, provided that's the only source. We're assuming only one source of uncertainty for that meter. In this case, we assume full correlation. between the U1, between each of the flows going into the flow meter, because it's being read by the same flow meter essentially. Using the roots mean squared method would give an underestimation of the total uncertainty. As I said, you can go into more detail in the GUM on uncertainties and look at things that are partially correlated, etc. But a good starting point when you think things may be related, or measurements that are related to one another, is to look at what the effect of no correlation is and the effect of full correlation is, and look at how that affects your overall uncertainty. And we can take a look at that now. Suppose the calibration uncertainty for the diameter and the height are correlated, in this case with assuming full correlation. We will essentially sum the UC squared terms together, so we'll add 0.955 and 0.905 together, and after we do that we will square that value to give us 3.475. And if we work around our stages all the way down and back across, you'll see that your uncertainty value will be 4.136 as opposed to 3.188. So it's increased, and it's increased because we can't take credit for the fact that the measurements aren't independent, and because these are the two largest sources, and we know if they're fully correlated, they're going to be out, or the uncertainty is going to be the same way, the true value will be the same way, it's going to increase the overall uncertainty. So hopefully that provides a bit of information on correlation, and perhaps it lets you consider if anything like that is relevant for your processes as well. So just a few points to summarise on the handling calculations. Always convert to standard uncertainty before performing them. It's just easier that way, and particularly when you've got different distributions. Ensure the units are identical for your calculation, and also for your sensitivity coefficients. Always round up. Probably less of a relevant point now that everyone predominantly uses Excel spreadsheets to do their budgets, and they will do that for you. And although these can be fairly detailed calculations, a good check is asking yourself whether your calculated value feels right. So is that about what you thought was the uncertainty in the value? So measurement, in summary, it says measurement is meaningless without a statement of uncertainty and associated confidence level. If you are performing a measurement, an important measurement, and you don't state what the uncertainty is and the confidence level in that uncertainty, it's very difficult to use that value with any certainty, essentially. Uncertainty analysis, it can be time consuming, it requires careful thought. It's not easy to identify all the sources. I still find it very difficult and to identify all of the sources. There's always sources you don't know about. But if you do it right and you take your time and develop a budget for processes that require careful thought and are expensive processes, you will save money in the long term by developing an appropriate uncertainty budget. And that's my final slide. So thanks everyone for listening. I'll pass you over to John now.
Thanks, Dale. That was good. Quite a lot of questions to get through. So we'll do our best.
Yeah.
First of all, you hit on uncertainty budgets. Now, uncertainty budgets is something I've come across an awful lot. A lot of customers asking us over the years to do uncertainty budgets for them, to train them and show them how to do uncertainty budgets as well. But basic question: uncertainty budgets. What are they? Why do we need them? And how often should they be done?
Okay, yeah. Essentially, an uncertainty budget, if we look at our practical examples, we have uncertainty budgets for our flow facilities. So what this does is look at the reference instrumentation, whether it be a primary standard or we're using a reference meter. And essentially, we go through the process, as I said, looked at in the practical examples. We determine all of the uncertainty sources in our facility and work out what that uncertainty, the overall uncertainty and flow rate of our facility is. Without developing these budgets, there isn't any credibility in our testing. If a customer comes to test a flow meter or other device, we need to have live uncertainty budgets or active uncertainty budgets to state that this is how accurate our facility is, and we can assess your meter against this uncertainty level of our facility. The final point was about how often should you look at them. I think it depends. Depends on your reference instrumentation you're using, depends on which form of standard you're using. But anytime, like in the example of the volumetric tank, you should know what your main sources are for your facility. And you should there are some sources that could almost be 10 times larger and they won't have an effect on the overall budget. So it's just using a bit of knowledge of the facility as to what the main uncertainty sources are and understanding how they may change over time, and that will dictate how often you check for uncertainty or recalibrate various devices. So it's having knowledge of the particular facility and the main uncertainty sources that will affect it, and not wasting time. Looking at things that aren't important. That's something I've made a mistake when I first started looking at uncertainty, was wasting time on things that aren't having an effect, even if they get 10 or 100 times greater. It's looking at the main sources and making sure that you're solid on them.
Yep. And checking those standards for any changes as well, I guess.
Yes.
Good. Okay. You mentioned the example on the tank volume. Got a question here. What is the basis for determining K? This question came in round about slide 62, 63, so I'm assuming it's in reference to that slide. So what's the basis for determining K?
Go back and have a look. The K factor.
Yeah.
So the basis in this. The basis in this is essentially dependent on your distribution.
Sorry, Dale. I'm just.
Yep.
Sorry, Dale. We're out of time, mate.
Right.
We'll need to. We'll respond to that question directly. Okay. Thanks again for joining us. As mentioned earlier, you will be getting a recording of today's presentation. Please get in touch with us if you've got any webinars or subjects that you want us to cover in future. We'd love to hear from you. Feel free to get in touch with me directly or send any queries to info.uk@tufsud.com or visit us on the website at www.tufsud.com/UK. On behalf of myself and Dale, thanks for your time and enjoy the rest of your day.